guess. You probably should be able to see everything, I guess.
Yes.
Okay, so I guess we can start. Okay, so today I'm going to be mostly talking about internals of Scala Native and how it mostly works, and how is that possible that when we write this high-level code in Scala, it is actually translated to a native binary, and how it happens. So of course, let's start with demo. Of course, that such things are possible. And when we have a simple hello world, we go through some steps, and finally we get some final binary, which of course is an actual native binary, which can be run somewhere in here, which is a native program. But so in some general, the whole pipeline, how the Scala code is transformed into this single executable can be basically shown on this graph based on some sources, which are going to the compiler. It produces some special files called native intermediate representation, which are somehow similar to bytecode in some cases, in some other cases a bit tasty, because they contain all the informations we need to later and which are easy to transform later into the format used by the LLVM. So the our targeted platform or the backend which are using. Later we have some linking stages, which just links all these dependencies from the compiler and some dependencies, optimizer as always, and some magic steps, after which we have an output in the form of LLVM IR, so the output which can be used by the Clang compiler or the LLVM backend. And from that point, it produces hopefully produces some good binaries. So let's take a quick look how it actually looks like. So in the target of our project, we have a bunch of files. So we can basically see how actually the LLVM IR looks like. So as in case of some method, it basically looks like some definition of something. It can be either define or declare, depending on the if some implementation is already present. And we have some number of inputs. In that case, it takes a single pointer to a byte and returns the same type. And we have the body. The body is basically a set of blocks or maybe a labels, depending on the context. I want to typically refer to these as blocks. So each block contains some amount of constructions. And if we take a look, BR is the instruction which conditionally jumps to some other block or label. In that case, if some condition which result is saved in this assignment is true, it goes to this block. Otherwise, it goes to this block. So as you can see, basically a very single operation, except these jumps, produces some value, or at least from our perspective, it produces some value. And this identifiers needs to be unique in the scope of the whole function which are you trying to use to define. Why it's important? I would say a bit later when we would go to the compiler, Scala compiler plugin where we produce the linear. But there's the LLVM IR. However, in most of the work, if we also, if we take some deeper look, it uses a lot of like very low-level operations which are not well defined. For example, this phi. Phi is an LLVM operation which takes, which basically is like an intersection node between multiple blocks, and depending on from which branch we are coming, we get some other results. It's kind of hard to work with something like that, I guess. And normally we work with our own intermediate representation called native intermediate representation, which is similar to LLVM IR. It also like is let me just run this color syntax. It also like has almost the same structure, so some definition, some mangled name, list of arguments, and set of blocks, basically. Again, so basically the same stuff. However, we are not using this LLVM specific operators or methods, but we make it a bit more high level, I would say. And we would only transform all these blocks to the LLVM IR in one of the last phases, but we might talk a bit about it a bit later. So again, we have these single assignments, which are unique, and however, in the LLVM IR, we had all these like only the pointers, etc. We have, but here we, for example, have the wall definitions of arrays or something of the wall types. For example, we have a definition of a class test, and all of its parents, for example. So an IR already consists of the hierarchy of types. Most of the things which might be needed, also like all the fields that are used and that are defined in a given class. And as I said earlier, names are mangled, so they typically consist of 2 elements. Probably better I would go to definition if in our code. So we have either the main type of identifiers is a global, which can be either a top name is typically a name of the class or a module, and a member. Member always has some signature and is always, here's the member, and is owner of some other global. And signature again can be, for example, one of the field, method, taking some types on the scope, constructor, or some external definitions, etc., etc. All of them are mangled, and they're mangled mostly because the namespace is completely flat. So I mean, so all the names are basically living in the same namespace, and without proper naming, we might get to name clashes. But okay, but we have this NIR, and between NIR and LLVM IR, so this representation which can be consumed by the Clang compiler, we have basically a wall node, which let me just find a place where the magic happens. So, for example, when we have some function definition, for example, which can be either a declaration if it's not implemented, or external, or definition, definition. We basically create the header. We basically translate LLVM IR, which as you have seen are very similar, and just adapt it to this textual representation of LLVM IR. I guess it's pretty confusing in naming sometimes, but it works, I would say. And basically, we've had definition, we have this header, or some other metadata which we'd like to use, and then we basically iterate over all the blocks and basically do the same. So rewriting an error to LLVM error. But how do we even get this an error? So the answer is pretty simple. We ask the Scala compiler to produce it. And as we are in the Scala Native project, in Scala Native it's implemented as a dedicated phase in the form of plugin, compiler plugin. It's very similar to how the Scala.js does it. However, in Scala.js, it's already embedded into the compiler because it's much more stable, and we are still at the stage where it's highly experimental and may change. And basically, native Scala Native plugin consists of two phases. One is interrupt, or a phase which happens at the very beginning, is injected somewhere after the typer and before pickler. So in one of the transform phases. And here we basically just introduce some small changes to the code. For example, add some annotations for some top level, external definitions. So for example, if you have, like in this case, some code, you can basically create some kind of binding to external functions. I don't have imports here, but basically it should work. In Scala 2 it was not working because we had no top level members. And also, for example, here's another case when we populate enumerations from the Scala 2. They're not really needed, not widely used in Scala 3, but sometimes they might be needed for some interrupt. So because normal ones are, as far as I remember, are using reflection, I think, to populate the fields. And instead, we populate the fields at the compiler time. But let's go to the main phase, which actually is called Gen near, so Gen native, generate native intermediate representation. It basically is starting, it should start somewhere near the backend phases of the JVM. So similarly to the generation of bytecode for the JVM. And we of course want to run it as late as possible. So all these, for example, transformations in the code would already be done, and we would be safe to use all of the work of the Scala compiler. And besides some settings which we have, we basically have one big class which takes some compilation units and just for basically collects all the type definitions. So type definition again is a class or a module or trait, and we only bother about these definitions. And for each of them, we basically go through the long process of transforming it. So again, looking for the, so basically transforming all the STs, or maybe not transforming, but traversing all of the Scala ST and getting all the needed informations. Okay, as we're here, here at the very beginning of generation of the class, we get into some interesting thing, which are the scoped variables which we are using. It's quite a nice trick which we use to manage the access to some variables and to make sure that they are cleared after leaving some scope. But while still making them quite easy to clean and control their scope of usage. And as you have seen in this example of textual representation, we have these identifiers. So number 2, number 3, number 1 for the agreement, etc. All of them basically are generated. Where is that? Near stat. By this fresh class. Fresh is, I would say, some type of stateful iterator, which gives us the next IDs of the identifiers. So we can typically start from the 0, but in some cases, for example, we can continue adding the new identifiers based on some previous instructions that we have produced. As we're already here, let's take a look at what can be an instruction. So in the new, now we typically have a few type of instructions. So maybe before instruction, to make it clear, we either have definitions, which can be, for example, a variable. So a definition of some variable field. It can be a define. So definition of a method can be a const, for example, some constant value. As well as it can be trait, class, or module, for example. And if you go, for example, to the definition of a method, it consists of multiple instructions. This instruction, for example, is a label, so a start of some block that we were seeing before, some let, so a single assignment. So in case of the example we had before, it would be this assignment to some identifier. So that would be a let instruction, where you have identifier and assign it to some operation which you do. And as well as some other mostly control flow values. So returns, jumps to some labels, some ifs, switches, etc., etc. So which are basically the base blocks are built in the program. Why we don't? You may ask why we don't like have it in the form of the AST, so it's easier to read, for example, on Traverse. Well, it's mostly because of how the LLVM IR looks like, and simply because by matching it, it's actually sometimes a bit easier to work with it and to transform it later. So that's the main reason why we don't have this nice ASTs from the Scala or in Scala.js, which also has them, because simply they're a bit easier to work with. And for example, and coming back to the instructions, instructions, for example, typically are some low-level operations like calling some method, loading, storing, extracting something from some structures, and very widely used stack allocating some values, for example. These are like the low-level operations that we can use. We also have a lot of high-level operations, which are defined mostly for an easier working with the code, and for example, introducing some optimizations, because as we can expect, class alloc, for example, would not consist of a single operation, but rather calling, for example, the garbage collector to allocate some amount of memory, then calling class constructor, and then only returning the created value. So by introducing these high-level operations, we can a bit easier optimize some of the things in the optimizer. So it's mostly for a bit easier work with that. And let's go back where we left. So we have this generate class method, and inside typically would get some attributes. Attributes are some additional informations about the methods or the classes. So, for example, we get information, for example, if given class is abstract or if given method is abstract, we get information if this method is really implemented or is it only a step that we just want to pass the compilation, but it's never actually used, for example, or some additional information. For example, we have a nice trick for forcing linking some external libraries using @link annotation used on some objects. And it forces later in the clang to actually link some external libraries that can be found somewhere on the path. So these kind of things are also like extracted somewhere from the class annotations, for example. And also we get all the informations about the parents or the traits of given class. Okay. So now we are in the near generate stat. So, or rather, generate statements. So statements like classes, methods, fields, etc. And that's what we do a bit later. So later on, for example, we iterate over all the field definitions of a class and give the appropriated definitions so that can be used later. Similarly, sometimes we also like to in order to for better interrupt with how JVM works, as we want to sometimes replicate some behaviors. We also generate statics or some static forwarders for some cases. In some cases, and typically they are created either for the fields or methods. Yeah, mostly for fields or some static methods. And here's some example that, for example, here we are creating a static getter for static field. Okay. Similarly, we do something very similar with all the methods. However, like in case of fields, we are only like creating some variable in our namespace, and typically just initially created it with default with the zeroed value. So in case, for example, of integer, it would be a 0. In case of some reference type, it would be null. However, in case of methods, we don't only create some top-level definition of consisting of signature, name, and attributes, but we also need to define a body of the method. So how do we do it, actually? In most cases, we do basically the same. So we traverse the ST. And actually, it comes with a few parts. So first, we generate the entry. Entry is basically the first, basically the list of arguments the method takes. So they can be actually used and referenced from within the body of the method. Then we, at the very beginning, create some fields for mutable variables. So if they are used inside the method, they are created or allocated at the very beginning. We always are sure that we can assign something to something that already exists. And then, of course, we have the body. And in case of traversing the body of the method, we need to go to another file, which actually does not produce statements, but rather expressions. And this is done in the new generated expressions class. So it's about still on this whole generation stuff. And basically here, in one very big generic method can expression, we do delegate to actual implementations for each type of Scala ASTs. So for the assignments, so that would be assignment of some new value for some immutable value, generation of blocks, closures, etc. Each of them has some dedicated method which does all the heavy lifting for us. And which one can, for example, show maybe unblock. So in that case, a block can be either like a match block. So it would have this case level definitions, which we need to extract. And sometimes sometimes it can be just a regular block having some number of statements we should also traverse, and we return the last value. If we take a look at this, it basically looks the same as some of the methods that we have in the plugins by themselves. So if we, for example, go to the standard plugin, I guess, no, not here, but there should be all these transform methods as far as I remember. I'm not sure in which it should be in a phase, if I remember correctly. Yeah, in a phase we have this also something very similar. So we have these transformation identifiers and prepare functions and transform functions for each of the ASTs, and they basically do the same. In theory, we could potentially use them, but the problem is they don't. They return 3, so they always return Scala ST. Which is not very useful for us because we typically want to get the produced new value, which can be then later, for example, assigned somewhere else. For example, if we have a call to a function, which is an expression, so in that case, we'd go through the apply block. Is that here? We don't want to like in return receive another AST that we would need to traverse, but you want, for example, the result of this apply function, and that's, for example, why we use some other dedicated stuff for that. Okay. So at this point, basically, this wall class new generated expression is basically in most cases very similar to implementation which we can find in Scala compiler for Scala.js. The only difference is that it's a plugin, there it is embedded in the compiler, but it does exactly the same job. Traverse the ST, produce some new intermediate representation. Probably in at some point in a time, hopefully Scala Native would also move all this implementation to compiler itself. So it would be always available, for example, with native versions, Scala, etc. Okay, we are speaking about the generation of expressions, but we have not said anything about types in Scala Native. So again, most of the stuff is pretty straightforward. We again have some primitive types like booleans, pointers, etc. So we also need to map all the things from the typical languages types, basic types. However, we have some specific types. I'm not sure if it's merged here already, but for example, to support, for example, 32-bit architectures. we had like recently added a support for having a new type of primitive types, which is link time based. It's this size type, which depending on the link time properties. For example, if you are targeting regular x64 processors or some 32-bit architectures, it can depend in size. But in most cases, we have just regular fixed size, for example, integers like in here, which have exactly the same size on the JVM. But what is a bit more interesting is some representation for some native, so the native arrays, which are basically just a chunk of memory without any overhead. So that's fixed size array in that case, which just happens to contain n elements of some type. And otherwise you have some also like structural types, which are again are not like classes, typical classes, which also like have a lot of metadata, but are just again chunk of memory that is populated by some fields. However, these are not widely used, and the thing that is the mostly seen in the type system is the reference types, which are basically in most cases reference to some kind, for example, reference to a string, reference to some class foo or something like that, or an array of such things. There are also like some additional types, but these are rather only handled internally, I would say, especially, for example, inside Optimizer, for example. Okay. So again, so how do we actually get these mangled names? So as I said at the very beginning, we have all the names inside this connective needs to have a mangled identifiers, which consist of this top level owner of some definition, and its signature which would be unique within the type. And for usage of that, we have this dedicated that's a Scala source base. We have this dedicated class, which, of course, depending on the type of some symbols. So names are created based on the symbols of some identifiers. Again, delegate to some specialized types. And maybe let's take a look at how methods are generated. So in that case, first of all, we have these native identifiers of a symbol. So in most cases, it would be just a simple name of a symbol with some mangled names in the same way as it is done on the JVM. However, there are a few exceptions from that, and the most important one are externs. For example, which always use exactly the same symbols as the name of the field of the method in which they were defined. And also we have some special overrides for some basic types like object class. Okay. However, it's very common in Scala to have different names of the methods which we use in our code, and typically want to have a different name inside our final code. we typically use it for that, this name annotation, like in here, which I guess it's very similar to the annotation called, I think, target on the Scala, when we, or the target name, where we define how the actual method should be called after the main. And we have something very similar. So for example, we have this platform object which defines some bindings to our external code, which is defined in C. So in terms of native code, we need to always make sure that the names are unique, and that's why we, for example, need to come up with some long descriptive names, which are hopefully not going to clash with some others. However, when we want to use it, we typically want a lot simpler names, and want to take advantage that we have simple objects, and we can refer to that. So in case of such cases, we have this name annotation. And so if some method is, for example, annotated with that, we would internally use this name always. So that's where such a things can change. Why it's important? It's important because, for example, in case of this method which we were seeing just a second, the Clang compiler would try to look for the name that was used in this at name annotation. So if we would have, if the Clang compiler would not find some symbol, it would of course fail to compile. That's why we need to make sure that names would be consistent, and otherwise it will fail. Okay. Let's maybe go back to the this big class which is used for generating the code. So let's assume that we have already traversed all the classes that we have inside the Scala compiler. All of them are typically stored in some mutable buffer, which we have somewhere over here. And what do we do next? We need to somehow write all these created new statements somewhere on the disk, and we need to do it in some consistent manner so we know where to look for each of them, and to make sure that they make sense, so they are easy to look up. So in our case, we typically all these generic definitions we typically try to group by their top number. So for example, all the things that have the common owner would be written to the same file. I guess that's exactly the same case that we have on the JVM, because on the JVM we also have all the methods of one single class stored in a single file, which of course makes the later class loading a lot easier. So we just, in that case, group everything. The second case, this one, reflective instantiation buffers are, I think we are not going to talk about them much today, because they are very specific stuff, which is only used to mimic reflection, which in both Scala.js and Scala Native is not really supported. But for example, there are some use cases which unfortunately needed to be covered. For example, usage of JUnit in the tests, which happened to be a basic and common testing framework for both Scala.js and Scala Native. But in general, somewhere in this under big chunk of code, we generate some forwarders, which allow us to either to create some instance of some class, or to load some module using some dedicated API in the native library. Sorry. Okay. So as we have grouped all the files together, we typically just dump all of them to the file, and basically our job in the compiler plugin is done. We can just take a quick look how serialization is done, but I guess it's not really interesting. However, just to have a quick look up how binary form of an IR might look like. So we have at the very beginning just some metadata, mostly containing information about the version of this Scala Native used, which this current version of the native intermediate representation that was used to produce this file. We have some file names so file names of the files that we are serializing. So in most cases, I guess it will be a single file which is matching a single compilation unit. And then we basically put positions of the definitions and write all these instructions, operations, and declarations based on some predefined format. So typically some identifier, what are we putting, so we know how to deserialize it, and in some established order, for example, attributes, and all the stuff we need, as well as instructions. Okay, so at this point, we would typically have this NIR created, and that's the part that is done by the Scala compiler. The next part is typically it's done by the build tool. So after all these sources have been compiled, we get to the second stage, which is a linker. So we take all the NIR files that have our compiler plugin produced, and would take some external dependencies. For example, we use some libraries. Libraries would also contain this produced NIR. Also, as we are here, if you look at the generated code, as the compiler has done all of its work, we can find regular files that are well known, so the classes, class files and tasty, as well as the NIR files. And if you would publish our library, all of them would be shipped together. So that's how we can use this NIR produced from other libraries. So the next stage is typically the I would say class loading, but ahead of time class loading. So based on some number of entries, typically it's just a single main method. We would try to find the definition of that method, for example, And when we do it, we also typically create some additional, a bit more richer metadata. It's stored in these info types. And they can be like, again, either, for example, information that we are dealing with a trait, with a classes, or with their members. However, at this point, we just start to collect information about which methods have actually been called when performing this class loading. So let me find this very start of this. Global. Guess it's not here. Which global? No. Sorry, I forget where exactly that part was done. In which entry? Let's just sum up. Anyway, summary here, there should be a call to which should try to perform a lookup. I think I found it. Yes. So based on this identifier that we have, so for example, let's assume that we have started looking for the first entry, which would be our main method. So we would try to find this mangled name, which, for example, would be something like test d4, so method having a 4 characters main. And we have this class loader, which typically, thanks to the fact that the names are have like a strict order, and we have these separators, similar as we have on the JVM, we can easily find it. Hopefully find it. If it's not found, of course, we'd have need to report it later and to fail the compilation. However, typically, we would try to populate our environment that we are creating with the collected methods. And we would also try to traverse it, for example, to find if it contains some signatures, some method with a given name, or otherwise, if it would be missing, we would typically try to, for example, find the position where it was called, so we can estimate at least where the given call was made. So it's even easier to debug. However, when you get to, if we will actually find this definition, we would typically need to traverse all the instructions, for example, and typically assign the instructions. We would come up with some new identifiers, so some new globals. For example, in case of our simple hello world, we would find a call to Scala predef, and we don't know what that is. So in that case, where is that? Not here. Anyway, if we would find some type that was not yet that is not yet known, it would be like added to the list, and it would be used in the next, for example, iteration in order to find it. Okay. So, in a short, that would be like a top-level explanation on how, for example, this part would work. So in this linker stage, we would typically just perform class loading and traverse all the things that we collect. However, also at the very end of this stage, we would do also do some tricks that we use, for example, for Scala Native to allow it to work on either Unix systems like Linux, macOS, but also which allows to compile it on Windows, which has completely different set of libraries and under some a lot of some external methods that might need to be used in either of them would not be reachable by us. So we have a very interesting trick here, which are like in link time if conditions, and I was maybe try to show it how they look like. Let me just find them. So we have a set of link time values. So you have a dedicated object where we define some of them, and inside at the point of the definition, they basically are just to nothing, or rather just throw undefined error. So they're not very useful, especially on the JVM. However, thanks to having this type annotation and having this name of what we expect to these properties being named, we can do some nice tricks, and that is inside the reach. We have this special type of if, which is called link time if, which consists of special type of condition, link time condition, which would be resolved only on the link time. So on the JVM, we have one of two choices. Something could be resolved either at the compile time or at the runtime. We have a third option, which is at the link time, so the between of the two. And what's interesting in that is if conditions that we have in here defined would be resolved to true, then only the first branch would be taken, and the second one would be completely erased. It would look like it would be never defined. Otherwise, we do the opposite. And let's take a look how they're used and why there might be a problem. Let me just find some usage of these link time conditions. Not this one. The ones we are seeing here are the regular runtime methods. That's why I'm not very interested in them. But that, for example, that might be a good case. Okay. So, for example, we're now in the Java standard library implementation of file, so Java IO file. And in that case, we want to know if some file is actual file or maybe a directory. And what's the problem? So on the Windows, we have this file attribute is set. No, not this one. We have some native method inside the which is only defined on the Windows, In that case, it's kept file attributes and something. But on the other platforms, we are using stat from POSIX stat library, which in that case is never available on the Windows. So even though, for example, in that case, it looks like a regular if that would fail on that might be resolved at the runtime, it is using this link time property, which is populated somewhere in the build tool, so we know how to resolve them. So if you are Windows, this part of code would look like it would be only this, and everything else would be removed. Why it's important? It's important because otherwise, if you would have our regular code, at the time of linking, both of these paths are possible to be taken. So typically, when you have a code, we can go, since it's a runtime check, compiler would expect that it can execute either of them. Of course, it would be easier, with, for example, with some inline ifs from the Scala 3, but our standard Java library implementation is cross-compiled to Scala 2, so we need to come up with something different. Yeah, and actually that would not work, because again that will be a compiler time, and we need to ship a single library which might behave a bit differently depending on the system. So at the runtime, if you would, for example, run it on Linux, as I use, while performing the reachability phase, so this linker, we would also visit this branch and come up to this external method, which actually would not be defined, because would not have its implementation anywhere when it comes to the compilation with LLVM compiler. So as we are in this reach method, which is our static reachability phase, we have this link time ifs. And let me give brief descriptions how they are used. So okay, so it's already here. We have this class which is already like pre-populated with some well-known system properties, which we can assign the build to resolve. And for example, if we come up to an if, for example, so this link time if produced by the compiler, we would try to add the link time having this set of conditions, check if this condition is either true or false. Yeah, here's this one. We would resolve the conditions, and if it matches, so if it was resolved true, we would only jump to one of these branches. So this whole statement, same time if, will be replaced with a single value consisting of a jump. Later, the untaken path will be completely removed, because we have also one port I have not said before. We have so-called control flow object, which defines this method remove dead blocks. What it does, it basically traverses all the blocks in the definitions and that checks which of them are reachable, so which are called from other ones. And if some blocks are never visited, they're simply removed after all. And basically that's what would happen in our case in these link time conditions. So only one path would be taken, the other one would be never actually loaded. And finally, all the references of this block would be completely removed, which would later look like some parts of the code would be completely missing and would not cause any problems. Okay. Okay, so we had a brief comparison of the compiler, had a linker. I guess I'm not going to speak much about the optimizer because it's completely Scantic related, and it's one of the most complex topics. We have basically two things left. So we have this lowering and code generation.
I'm sorry, Wojtek. How many do we have still to cover? Because we're already past the 1 hour mark. So.
Oh, okay. Yeah. Oh, sorry. Okay. Yeah. So I guess let's just take a quick summary and let's finish basically. Yeah. So after like this code comes up from the optimizer, it goes to this lowering. And for example, as I said earlier, we had this like a high level operations, like for example, class allocating consisting of like few things. And somewhere at this point, we like translated to a set of simple operations. Yeah, like we have all this set of these high-level operations, like let's like accessing some field, which is typically just loading some pointer based on the field. And we just replace it in our final NIR, which will be then translated to LLVMIR. And also in this last stage, we actually do something more important. So we, for example, have this, we build actual memory layout of our classes. So we know where each fields are inside the code and we can reference them like fields layout, etc. And as well at this point, for example, we can generate calls to some specific stuff. For example, when you run class of some type, it would be like at this point duplicated if any of them exist, and we'd have only one reference to some class or some class object of some type. Okay, so I'm not going to take much longer. I've showed you at the very beginning a bit of the transformation between IR and LIVMR. So it's only like rewriting one format to the other, and then all what is left is basically just passing everything to the Clang compiler, and it hopefully produces some final binary. I just wanted to show you one more thing, which are like overrides of the standard Scala library. We have last time some kind of patch mechanism. So for example, there are a lot of things that are not possible to easily implement on the native side. For example, lazy balls, which were like using some unsafe methods to get some offsets. And for example, in this Scala Native, they are like completely removed. In one of the phases of the compilation, we rewrite them with our own implementation, which, for example, takes just a pointer, which just calculate in some other way, which is not using reflection at all. So that kind of stuff can be found also in our Scala lib, and that's why sometimes something might behave a bit differently. But anyway, I guess we can finish now, unless there are some questions.
Thank you very much, Wojciech. One question that I had is like maybe not too related, but I saw in one of your commits like the highlights. So how many people are currently contributing to this project? Because I saw like some commits from other people from a couple of months ago, and I was assuming that you were the only one working on it.
Okay, so in general, I think there are 2 or 3 constant contributors, which, for example, are Eric Richardson and some guy called Lee Tybert. I'm not sure if it's his real name or not, but these are the guys that are very mostly handling some POSIX integration stuff. They have a good knowledge in that area, and I've seen that they typically work somewhere in here. Right now we have like also like a student working on the Google of Summer of Code program on some of work on this Scala Native. And also there's me, which is mostly trying to finish multi-threading support in my free time, and hopefully it would be merged soon, as it is already like quite usable, not yet finished. So I would say like 3 to 4 people working on it, but in a free time, I would say, mostly.
So also great that it's getting some traction among the contributors.
Yeah, that's true. Also, like now, for example, part of my my job here in Virtus Lab is also like maintenance over here and dedicating some amount of time just to development on this Scala Native still, which still has a potential, in my opinion. But of course, there's a lot of things to do.
So what are the main things that you're working on these days? Like the main problems left to solve, or the main things that you're working on?
Okay, so I'm mostly working on the multi-threading part, and in that area there are 2 things to do. So I mean, one part was basically adapting the existing garbage collectors to because we have our own implementation of garbage collector written in C, and before they were not concurrency aware, so there was no synchronization, for example, between them. For example, in terms of allocating some blocks of memory or stopping the word. So that was one part which was mostly done. And the second, in my opinion, more cumbersome topic is implementing all of the multi-threading primitives back to the Scala. So, for example, there is an JSR 166, which can be safely ported to the Scala, which was written in a Java and merged many years ago, which is still developed sometimes. And for example, all this stuff like fortune pools, all these re-entered logs, atomic classes, all that can and should be ported. A lot of them is already done. However, I'm still having some issues at runtime, for example, in some of the tests. And it's not always as stable as I would expect it to be. So that's the main area of the main work right now, I would say.
Mm-hmm.
But there's a lot of other topics.
Yes, thank you, Wojciech. Any other questions?
I have a question about the testing strategy. you showed that Scala Native is a number of components. So do you test each component individually? Like, do you test the compiler, or do you test all of them at the same time?
Okay, so in terms of compiler tests, we have a bit of tests for that, but they're not very rich. I mean, inside the project, we have some here. We have some tests that, for example, check that the generated NIR was correct. Oh, here. So I would say that there is mostly some set of some basic stats, some name angling, etc., as well as, for example, compilation. I would say something similar to the Scala positive tests or Scala negative tests from the .t repository. We just check that some code compiles or it does not, for example, like in that case, or that some features work as expected, for example. So it's in terms of compiler testing, it's not very rich, but since most of the actual tests are testing runtime at this point. There's a lot of tests which are mostly targeted for the checking of the compliance with the of the Java standard library mostly. Yeah.
Okay. And do you have a community build to test Scala Native on many libraries?
No, not yet, but I have a plan. As you maybe have knew, I'm like working on the community build for the .t. So, and based on the experience from that, I guess it shouldn't be that hard. But the problem is that similarly with Scala.js and native, it does not only use JVM, and we typically need to install some external dependencies, which might depend on the project, and it's a bit harder to make sure that all the needed stuff would be present. So, but otherwise, I think if I only had enough time, it should be possible to make something in the future, but not now.
Okay, thank you.
Thanks. Okay, so I guess if there's no more questions, I'd like to thank you for today.
Yeah, thank you, Wojciech, for the detailed overview.
Yeah.